Okay, I'm just going to start this. I'm starting a little bit late, but not a little bit late, a lot late. But I'm just going to start it anyway because I can't seem to make the projector work here. Which means I'll be doing a lot of things on the board behind me. Which I suppose is better than nothing. So I apologize in advance if you can't see everything that I'm doing. I'm going to have to go back and forth quite a bit. Okay, so anyway, this is what we're starting with. Here is we're going to start by learning about what is potential and how it's related to potential energy with an electric field. Eesh. So, what you're seeing at the very beginning of the chapter here is you're seeing something that looks like this, where you have two plates. The one on the right has a hole in it. So if we were looking at this from the side over here, you might see like a wall of metal. And if you were looking at this side from over here, you would see a wall of metal with a hole in it. And this is not showing up all that well on the screen, so I'm going to put mine a little thicker so you can see them better. It shows up a little bit better. And the idea here is to put positive charge on one of these plates, charge it up, however, whatever method you want to use, but get positive charge on this plate over here. And since it's a metal plate, it will spread itself out nice and evenly. And then to get negative charge onto the other plate, whatever method you're going to use. And because of this, you will get electric field lines that go from the positive charges towards the negative charges, more like this between the plates. You get a little distortion of field right there, but for the most part, it will be pretty parallel lines between the plates here. And what we're going to do is we're going to put an electron inside this field, or some kind of electron or a positive. I can't remember what kind of charge. I think it's a positive charge they put in there, which would make more sense. Yeah, they put a positive charge in there, which makes much more sense. So they put a positive charge inside between the two plates in this field here, and they hold it there. They hold it in between these two plates. And it doesn't matter where you put it. I put it right there next to the positive plate, but you don't have to put it there. It could be somewhere else. It could be further over here, up here, down here, whatever else. It doesn't really matter where you put it. Just put it in there somewhere. So that it's between the positive and negative plates. What is that positive charge going to feel due to the positively charged plate? What's it going to feel from that side of the system? It's going to be repelled. And what's it going to feel from the negative?
It's going to be attracted.
It's going to be attracted. So essentially, it's feeling a force to the right. Right? It's feeling this force that's going from left to right towards the negative plate, and if it's in that center area there, it's kind of feeling a force that will eventually, hopefully, shoot it outside. This is how we use electrostatic fields to accelerate particles. Many, many particle accelerators start out with this kind of a setup, where you have positive charges or whatever, so it could be even negative charges. You flip everything around backwards. But you have something that's positively charged inside of a situation like this, inside some plates like this, getting forced from the positive side towards the negative side, and then if there's a hole in those plates, then it can go flying through those holes, and then all of a sudden you've got this free particle that is moving really fast. And you can do a fair amount of acceleration to particles like this. But we don't want to talk about necessarily the acceleration of the particle so much as we want to talk about the possibility of it accelerating, or its potential to accelerate. If you accelerate a particle, you give it kinetic energy. So while it's inside of this field but not accelerating, it's kind of like it has potential to accelerate. And in last semester's class, we called that potential to gain energy, potential energy. So being in a field for a charged particle in a field, it's like having potential energy. It is a type of potential energy. But how are we going to measure what that potential energy is? How much is it, for example? How are we going to figure that out? And that's really what this chapter is all about. It's figuring out what that potential energy is. Just below this picture in the book, they show a picture of a particle on a hill, like a ball on a hill, where the ball is at the top of the hill, or it's lined up with this one, I guess. So in this case, being somewhere between the two plates is like a ball being somewhere between the top and the bottom of the hill. It doesn't have its full potential for rolling down the hill, but it has most of it, right? If you put the charged particle all the way towards the positive towards the positive plates, it would be like lifting the ball all the way to the top of the hill, where that top of the hill is its highest potential energy. Okay. Now, in electric fields, we don't necessarily talk about potential energy so much as we talk about potential. And the reason for that is because, well, one of the reasons for that is because the bottom of the electric hill is not as easily defined sometimes as the bottom of a hill in a kinematic situation or something. Sometimes it's just not so easy to define it because sometimes you don't even know where the field is going. You're out in space somewhere and you can detect electric fields, but sometimes you have no clue. Most of the time you have no clue what is causing that electric field. You can't see the charges sometimes. Maybe the charges are too far away or too small or just hidden some way. But you can detect the electric field from those charges. So even though you may not know where they are or how powerful they are, you know that you're in a field that has some kind of a strength. And there is a way to detect, or a way to calculate how much potential you will have to do something. And the way that you do that is you assume that the particles, you assume that you're zero potential. You assume that the place that you will not feel that field anymore is infinitely far away from where you are now, which essentially puts you infinitely far away from whatever's causing the field, right? So it's a bit of a philosophical debate, but it works fairly well, mathematically. And if you assume that it's infinitely far away that you need to go to get away from this field so that you've achieved your maximum potential and that field is now zero and you've taken all the energy that you can from it, then you can actually calculate the work that was required to get you to where you were. And how can you do that? Well, you can do that. There are some calculus where you can do that, but you can also do it considering where you are to be the highest point of the field and where you're going to be zero field, and calculating the energy difference that you would get. And that would be your maximum potential energy that you could gain from being in that field at that point in time, assuming that you could get out of it in such a way that you would go to that 0 point field. And if you do that, then you calculate the amount of energy that you would gain from doing that. You would essentially be calculating your potential energy, your maximum potential energy. But because we don't actually know the charge that's gaining that potential energy, because that's another problem we have. The charge in that field is a big factor. What size charge is it? Is it a positron, like has a charge of an electron? Or is it a helium ion, which has two charges, which is the equivalent of two charges of a proton? So it could be different kinds of charges. So how do we describe a field without describing what charge is in it? Because remember, the field that is created and the charge affect how much force the charge feels. So we have to kind of think that through. And so we say, What is the problem here? Well, we need to get rid of the charge. We need to say that the charge is not something we're going to deal with. Now, what do you mean, get rid of the charge? Well, this is what I mean. Let me go back to my board here. When we were calculating the force that a charge feels in an electric field, the Coulomb force, right? We had this equation, K, which is the Coulomb constant, times the charge divided by R squared. And I said we need to get rid of the charge, but that's not exactly correct. What we actually need to do is kind of get rid of the distance. But anyway. So this is calculating the force, but if we wanted to know what the field was, that's when we got rid of the charge. We said that the field is only equal to K times the charge that is creating the field, not the charge that's in the field, so we remove the charge over R squared. And we use big Q in that case. So there's a charge that's creating a field, there's a charge that's feeling a field. If you get rid of the charge that's feeling the field, then all you're left with is the charge that's creating the field, and we calculate the field. So this calculates the force between two charges. This calculates the field that a single charge makes, that another charge might be moved by. And then how do we calculate this potential energy thing when it comes to this? Well, potential energy, remember, is equal to work done. Technically, it's equal to negative the work done. And work is equal to force times distance, right? And force, in our thing up here, is equal to this KQQ over R squared, right? And so we can kind of relate that in here. If we take the force that's happening over a certain distance, and we multiply by the distance, well, what distance is that? The distance is the R, really, as long as we assume that that R distance is as far away as it needs to be, right? And then we come to the point that we're interested in. So that actually kind of gives us a clue as to what's going to happen. If we go into all the details, we get a little bit mathematically intense, but in the end, what ends up happening is we get an equation that looks very similar to these equations, but is now multiplied by the distance that it was divided by in the square there. So we, instead of getting something over R squared, we get something over R. So let's go back to our book and take a look at this. So our potential energy is going to look like our force times our distance, so it'll be the K times Q over R squared, and then we multiply by the distance R, and we end up getting rid of one, so you get KQ over R. But remember, we still want to get rid of the Q. We don't want to be looking at both Q's, because we're not talking about the potential energy between two objects. We're talking about the potential energy, or we want to know about the potential due to a field created by an object. So then we do the same thing we did here, where we remove one of the charges by saying this charge here is not going to be creating a field that we're interested in. We're only interested in the field outside of this charge. Even though this charge does create a field, we're kind of ignoring it. And so we say, okay, we take our potential energy and we make something new, which we're going to call potential, which we're going to give the letter V for voltage, and usually we use delta V for change of voltage, or change of potential. And what we're going to do is we're going to assume that one of these charges is a test charge, and we're going to divide by it. We'll call this, the second Q we'll call QT for test charge. We're going to divide the test charge out. That's the charge that we put in the field. We're going to erase it so that we don't have to worry about its field. And we just get the potential energy, which was KQ QT over R, and we're going to divide by QT, so the QT's are going to go away, and we're going to end up with KQ over R. And just like with field, we're going to use a big Q, because we're just talking about one charge. We're going to say that's the charge that creates this potential. So that's what we're going to be dealing with at this point. This is what we call the potential of a field. And where did they put that equation? They put that equation here in and they show some of the calculus even a little bit. But they put the equation in, where is the equation? It's in the second section here, somewhere. Maybe not, maybe the third section. Yes, they put it in this third section here, where the potential is K times Q over R, and this is good, just like our electric field is, and our electric forces are for point charges. We haven't really done any geometry with this yet. All of our charges, everything that we charge up is like a point charge or a small sphere of charge or something. So that's where that comes in, right there is in the third section. But this is something that we call electric potential. It is the potential energy per unit charge of in a field. So it's the possible energy that a charge could feel if you put it in the field, if you multiply it by the charge. So how do you use this thing? This V thing, this delta V, this potential, this thing we call potential, which is related to potential energy. So that's what we're going to deal with. Since delta V is equal to the potential energy divided by the charge, if you want to know the potential energy of a charge in a field, then you take the voltage and you multiply it by the charge that you put in that field, and you'll get the potential energy that charge would feel in that field. So once you figure out the voltage, you can figure out the potential energy of any charge in that field at that point in space. So, let's see, let's go back to the book really quick. So let's look at some examples of what this is about to try to understand it a little bit better. Work through some of the examples. Good night. It's hard to use the computer when your pointy finger is not working properly. Okay, so let's look at this example is the one calculating energy. You have a 12-volt motorcycle battery. It can move 5,000 coulombs of charge, and a 12-volt car battery that can move 60,000 coulombs of charge. So when you have a battery that has a voltage, it's essentially a battery that has two different charges in it that creates a field. And that field can push charges from one point to another. So that's the idea. And you could visualize it. You could visualize a battery like this, where you have one side of the battery, which is the positive side, and another side is the negative side. And there are charges that it's supposed to push. And in between here would be all the electronics in the car. And you push the charges through the electronics in the car. And so we've got two different batteries. We've got a motorcycle battery and we've got a car battery, and they both have 12 volts, but they push different amounts of charge. One pushes 5,000 coulombs, the other one pushes 60,000 coulombs. We want to know how much energy each delivers. So here we have voltage and charge. And remember, we said that potential energy equals voltage times charge. So we take the 12 volts for the motorcycle battery and multiply it by the 5,000 coulombs to get the amount of energy in a car battery. 12 volts times 5,000 coulombs gives you 60,000 joules, because energy is measured in joules, and volts times coulombs gives you joules. And you're going to get 60,000 joules of energy in the motorcycle battery. In the car battery, you're going to have 12 volts times 60,000 coulombs. So a lot bigger number. It ends up being 720,000 joules of energy, potential energy in a car battery. So motorcycle battery, not a big deal. 60,000 joules, not that dangerous. Car battery, 720,000 joules. 100 times more. 10 times more, actually. A lot more dangerous. Don't want to lick your fingers and touch that battery.
DC doesn't transfer very
Well, it depends on the voltage. And also depends on the conductivity. If you lick your fingers, you've got enough conductivity to get that current going through your body. It'll hurt real bad. Yeah, a car battery with licked fingers easily can kill you. Because it gives you the conductivity. All right. I'm going to take a little bit of a break. I'll be right back. Got blank paper right back there that's blank on one side. On the top of that.
Grab something. Had all this stuff written down on what to do. That's not the track. Alright, so what's the key?
Okay. Do you have a class after this, Scott? Today? Do you have another class today?
Yes.
What time? 11?
No.
10? 2? 1? I just wanted to make sure I wasn't going to run into your other class. Okay, sorry for the delay there. So the next section, the next example says how many electrons move through a headlight each second. You have a 12-volt battery, so it's kind of like this battery up here, this strange representation of the battery anyway. And it's running a single 30-watt headlight. So watts, volts. Let's remember what volts are all about. What a volt is it's a joule, because it's a because remember that we took potential energy, which is measured in joules, right? And we divided it by charge, which is measured in coulombs. So this is voltage. That's voltage. Volts are joules per coulomb. So if volts are joules per coulomb, and we have 12 volts, then we have 12 joules per coulomb. So it's a good idea to kind of do some evaluation or checking of our units here to figure out how to do problems. If you have joules per coulomb, how are we going to do this problem? Well, erase some things here. If volts are joules per coulomb, watts, remember, are joules per second. They're how much energy we use per time. And the question that they want us to answer is how many electrons pass through it each second. Then we need to use these two things to figure out what? Electrons per second would be charge per second, so it would be coulombs per second. And then we would figure out how many electrons by dividing by the charge of an electron, right? So we need to figure out coulombs per second from these two things. What are we going to do to these two things to get coulombs per second? Well, we need coulombs not in the denominator, but in the numerator, right? So we're going to flip over the voltage, so we'll have 1 over voltage, which will equal coulombs per joules. And then we're going to do what with it? Multiply it by watts. So if we take watts and multiply it by 1 over volts, we get watts, which are joules per second, multiplied by 1 over volts, which are coulombs per joule. The joules will cancel out, right? And we'll end up with coulombs per second, which is charge per second. And then we can figure out how many electrons are going through because we know how many coulombs each electron is. Right? So we call this dimensional analysis, where we look at the dimensions of the units of our different things that we know and figure out what we're going to, how we're going to have to multiply or divide things to get our answer. In this case, we need to take power, which is in watts, and divide by voltage, which is in volts, or joules per second, and that is going to equal the charge moved. And then once we know how much charge is moved, we'll divide that, we'll divide the charge moved by the charge of electron, and that will give us the number of electrons that have been moved. And on that page in the book, that's exactly what they do. They take the voltage, which is 12 volts, running a 30-watt headlight, and they take the 30-watt headlight, which is the power, divide it by the 12 volts, which is the voltage, and they get negative 2.5 coulombs. Now, why do we put negative in there?
Because it's an electron with its negative charge.
Well, the reason is because, no, we're eventually going to divide by the charge of electron, which is going to be dividing by a negative number, and then that will, you're thinking along the right path, but that's not the reason, technically. It does give us the correct sign. But the real reason is because work is technically the power, and work is technically equal to negative the potential energy. And so we'd have to put in the negative voltage to get this right, or the negative potential energy to get it right. And so that's technically why it is this way.
So power divided by voltage equals a negative charge because electrons moving in the air.
Yes, because it's the electrons moving and not the protons and all that stuff that we've learned. It's Benjamin Franklin's fault. That's the reason. So anyway, the point is that, you know, if you want to do it mathematically correct, you get that negative sign in there. If you don't do it mathematically correct, you're just going to get a positive amount of charge, and you'll just still divide by the charge of an electron and know how many electrons we're moving. You can just think of it that way and not have to necessarily do the math correct.
So coulombs per second is a standard of measure.
Coulombs per second?
That's not something you're going to use mathematically.
Yes, coulombs per second is a unit.
Right.
It's not a number, it's just the units.
So E over I equals
And, you know, power divided by voltage is actually something that we're going to learn about later when we start learning about Ohm's law. Because power divided by voltage is technically current. So charge per second is current, which makes sense, right? We're just not talking about it in that way yet. Now, what if you take the charge and you multiply it by the voltage? We already decided what that means. When you take charge and you multiply it by voltage, it actually gives you energy. And when you're dealing with the energy of electrons, like the kinetic energy of electrons or the potential energy of electrons or other small particles like that, it's actually a good idea to use electron volts as your units instead of joules, because it's such a small amount of energy, even if they're moving quick. Because electrons are so small. Their masses are so small. So electron volts, it's just another way of measuring energy. It's just another unit for energy. 1.6 times 10 to the minus 19 electron volts. Sorry, 1.6 times 10 to the minus 19 joules is 1 electron volt. So 1.6 times 10 to the minus 19 joules, which is the same number for the charge of an electron, is also the conversion factor from joules to electron volts. So when you have your energy of electron volts, you have an electron at 1 volt has 1 electron volt of potential energy. An electron at 2 volts has 2 electron volts of energy. So it's a very simple system. If you know the voltage and you know the charge, you can figure out really quickly what is the energy in electron volts. It's just multiplying together. And so we use that a lot when we create. So for example, when I was doing X-ray research with X-ray tubes, we had electrons that were put in this tube, and we would turn the tube up to 40 kilovolts. So we knew that our electrons, once they came out of that tube and went through that electric field, we knew that they had 40 electron volts of energy, of kinetic energy coming out. So it was very easy to make that computation. Just do it in your head. So electron volts are just another unit of energy. Just like all energy that we've dealt with so far in this class, electrical energy is conserved. So you have the potential energy plus kinetic energy equals a constant. It's always the same. It just goes back and forth between kinetic and potential, kinetic, potential. And you can even have elastic energy with electrical, because you have this repulsion and attraction bit. So you can have elastic energy, kind of like spring energy. Electron bonds, for example. But if you have this always being a constant, then you have a kinetic energy initial and a potential energy initial equaling a kinetic energy final plus potential energy final, just like with our energies before. So if you know the kinetic energy of a particle and the voltage that it's at, and you know the charge of that particle, then you multiply the voltage times the charge for your potential energy, and you add it to the kinetic energy initial, and that has to be equal to all that stuff at the end.
All right, sorry.
Okay? Let me put my screen up here so I can make a nice picture of this. Since our stupid lame projector's not working still. I'll try it, turn it on again, see how it works for us. But anyway,
Potential energy plus kinetic energy equals a constant.
yeah, it's always a constant. In
So
other
if you don't
words,
know your constant, what do?
what's that?
Do you always have to know your constant?
Well, you always do know it if you know the potential energy and the kinetic energy. So you figure out your potential energy, figure out your kinetic energy, add them together, and that's your constant. But the real purpose of this is not the important part. The important part is that if I measure this at one point in time or space, or both, I can get, so that's my initial kinetic energy and potential energy added together. If I do it another point in time and space, later, in some other place, then they have to be equal because they're both equal to that same constant, right? That's the important part. That's the thing that tells us it's conserved. That's the law of conservation, is what it is. It's the law that says that energy is not created or destroyed, it just gets traded around, right? And so in this case, if you have kinetic energy and potential energy equal to each other when they're added at any point in space and time, then if we know, for example, that the potential, remember that potential energy is equal to voltage times charge, V times Q. And kinetic energy is just what it was before, 1/2 mv squared, mass of the charge times the velocity of the charge squared. If we know the potential energy at the beginning, we say that we know that voltage 1, or voltage initial, is VI, and we know the charge is just Q, whatever it is. And then we know our kinetic energy initial, let's say it's 58 joules or something, that's not very much. Maybe it's 58,000 joules. Let's say it's 58 kilojoules. So it's 58,000 joules of kinetic energy from its movement. And then some point later in time, it's moving at a different speed. Let's say that it's moving at, it's got a kinetic energy final of 202 kilojoules. And then we want to know what's the voltage at this point compared to this point. Well, the voltage here times the charge here, the final voltage times the charge is equal to the potential energy, right? But since we knew this one and we don't know that one, we can use this equation to calculate the last one, the final one. So let's do an example of this really quick so that we can kind of see it in action. I need to write this on a different point on the screen, don't I? Or move here I can move my computer. Unless you want it to stay still. What are you doing? Hitting the select button? It's not helping. Unfortunately. I'm on the HDMI, and it's never worked for me. Well, it's not never, but it gets into this mood where it doesn't want to. No, I'm not on computer. I'm on HDMI.
About network, that's why.
No, I'm on the HDMI.
That's where it is.
Yeah, and it doesn't even recognize that I'm there. It did at the very beginning of class, but then it turned off, and it doesn't work now.
See, there's why I wondered if it doesn't say project computer.
No. Here, unplug the HDMI cable. Right above you. Just unplug it and plug it back in. I think that's what worked before.
I gotta put it back in.
No, I can fix that from here. It's on HDMI. Just unplug it. Now plug that back in. See if it detects my computer now. Yeah, it's just being stupid. It's a piece of crap. Doesn't help. Anyway, we won't even try it anymore. It's not worthwhile. Okay,
so your voltage initial Q, that's your potential energy. Your K.
So this is potential energy initially. This is just our kinetic energy initially. And let's say that we know that our final kinetic energy is something bigger. That means this changed too. So we can figure that out by plugging the numbers that we know into this equation, solving for what we don't know. Let's say that our voltage at the beginning was,
Kilojoule is another unit of measure, right?
yeah, that's energy. So let's say that we have 20 kilovolts of voltage here. And let's say that our charge is an electron at 1.6 times 10 to the minus 19 coulombs. If we multiply these together and add them to this, and then solve for this voltage here, we will find out what this voltage would have to be to make that happen.
Now, why did you put a K in front of volt? Isn't volt the...
Because it's kilovolts, just 1,000 volts.
Yeah, but the standard is volts.
Yeah.
Right? So if there's, you would have to make them both for the standard unless both sides were kilovolts.
Yeah, so if this is 20,000 kilovolts, I mean, if this is 20 kilovolts, it's just 20,000 volts. Because kilovolt means thousands, right?
And what's the 1.6 is your fixed number?
That's my charge. That's the Q that I chose. It doesn't have to be a fixed number. It can be any charge that I put in the situation. So in this case, I just chose the charge of an electron. But let's actually do a problem that demonstrates this rather than just thinking of it theoretically. So in this example here, we want to calculate the final speed of a free electron. So where does the speed show up in this equation?
It shows up in the...
Speed shows up in kinetic energy, right?
Yeah.
In velocity right here. So it shows up here, this has the final speed in it, this has the initial speed in it. So it shows up in the kinetic energy on each side of the equation, here and here. And we're going to go through a potential difference of 100 volts. That means that our initial voltage would be at 100 volts and our final voltage would
V up
be...
there is velocity, right?
Yes, this V is our velocity. So there's two V's now. There's a big V, which is voltage, and there's a little v, which is velocity. Not to confuse you, but we're definitely going to be confused for a while. So voltage is always shown as an uppercase V. Velocity always is a lowercase v. So anyway, we want to calculate what would be our final velocity if we start from rest. So our initial velocity would be 0, so our initial kinetic energy would be 0, right? So if we're starting from rest and we're going through a potential difference of 100 volts, well, what does that mean in this equation? Remember that potential energy, let's look at the, let me get my screen here back to where I was. Oh, shoot. That's not what I wanted to do. Stop share. There we go. Okay, so my potential energy is Q times V. That's Q times V initial. My kinetic energy is 1/2 mv initial squared, but my initial velocity is 0. My potential energy final is Q times V final. And my potential energy final is 1/2 mv final squared, which is the thing I want to know. This is the thing I want to calculate. So I'm going to solve this equation for this. This whole thing becomes 0, so that's nice. We don't have to worry about that term. We want this thing, we want to calculate this V final using all the rest of this stuff.
Why do you do all that goop in front of it and make it go away?
This?
Yeah.
Because the velocity, the initial velocity was 0, and that makes this term become 0.
0 times.
Right? Because 0 squared is 0. So this is what this term looked like. It looked like 1/2 mv squared, and they told us that our initial velocity was equal to 0. So this is equal to 0. That makes this whole thing equal to 0. Right?
Okay.
That's why I did that.
Yeah, but initial should always be 0 unless it gives you a certain point.
Yeah, unless they tell you that it's starting at some speed, then usually you assume that it's 0. But that just makes our equation a little simpler. We're trying to solve for V final, so I'm going to subtract this from both sides, QV final from both, voltage final from both sides, minus QV voltage final. And I'm going to get Q voltage initial minus Q voltage final on the left side, and on the right side, these will just cancel out, and I'll get 1/2 mv squared, final squared, on the right side. Remember, I'm trying to solve for this V, so I'm going to divide by M and multiply by 2 here. And do the same thing over here. I'll divide by M and multiply by 2. This will be 2 over 2, so it'll be just 1. This will be M over M, so that's just 1. So the equation that I get in the end to solve for is V final squared on one side, and on the other side, I get 2 times this right here is Q times V1 minus Vf, so I'm going to actually pull out the Q, and I'll just get V initial minus V final, voltage initial minus V final, all over the mass M. Okay. And then to finish this up, I take the square root of both sides, because this is V final squared. Take the square root of both sides, and I get V final equals the square root of 2 times the charge over the mass times this difference in voltages. And the difference in voltage is delta V, which is the thing they give you. They tell you the difference in voltage or the difference in potential is 100 volts. So then in the end, I just plug in my 100 volts, multiply by the charge times 2, divided by the mass of the charge, and I get the final velocity of the charge. This should be a little V to distinguish it from the big V. So that's how you would calculate the final speed, which is related to this final kinetic energy here, of a charge that goes through a voltage difference of V initial to V final with charge Q starting from rest. And that's an equation you should remember, because, or write down, because you'll use it a few times for sure in this class. Really wish my projector was working so that I could walk you through this in the book with all the pictures they use and everything, but we're stuck. And I think more than anything, this equation illustrates what voltage is, because it kind of relates very...
Why did you change the order of the QV? You
Why did I
started out with
change-
VIQ and then you changed it to QV. I mean, I understand it doesn't matter, but
like this from here to here? I had no reason, I just did. Probably because that's the way it is here in the book, as I'm looking at the book. I probably just looked at the book and wrote it that way instead of the other way I'd written it. As I'm glancing back and forth from book to board, sometimes that happens. I try to do things as close to the way they do them in the book so that it's not confusing when you look at what I'm doing, but I don't always succeed. Anyway, I think that this kind of an example illustrates how what voltage is better than most anything else, because it helps us to understand that voltage is this potential energy that a charge would feel if you multiply that voltage by that charge and put that charge into that situation where it feels that kind of a voltage. And so you multiply the charge and voltage to get the potential energy, and then it can affect the kinetic energy as it goes from one voltage to another voltage. As it changes voltages, it will change kinetic energy. And in this way, when we're talking about these things like particle acceleration, it has very few applications that most people will encounter in their lives. You know, physicists will encounter it as they're doing experiments. Engineers may encounter it a little bit. Medical people will encounter it if they're working with a positron emission tomography machine or something like this, or whatever. But most people are not going to really encounter it much. But where but it is directly related to things like voltage and current and electronics, which is something that almost everybody encounters at some point in some way in their lives. And so this speeding up an electron from one voltage to another is exactly what causes current to flow. You have a voltage at one part of the circuit and a different voltage in another part of the circuit, and that difference in voltage is going to determine which way electrons flow, how fast they flow, how much energy they can impart in the electronics as they flow. That it has everything to do with how electronics work. So I'm going to go ahead and move us to the next section because we are going to continue to learn this stuff as we go on through the next sections. We're not going to be...
And that tells us velocity final.
Yep, we can calculate the final velocity when we do that. That's exactly right. So, how is voltage related to electric field is the next question. Well, it turns out that potential energy, which is voltage, we already kind of hinted at this, but we didn't really talk about it in great detail. But that voltage here, which is potential energy related to potential energy anyway, is also related to the amount of work that you would have to do to remove that charge from the field. So it's also kind of equal to work. We usually put a negative on there. Do they do that in the book? No, they don't really do it.
Yeah,
No,
they do.
they do, yeah.
I think it's work equals negative potential.
Yeah, they do it the other way. They do it this way. Work equals negative PV. Same thing. Negative change in the potential energy. And this would be Q delta V here, right? So they do that in the book. And essentially what they show in the end is that the work is equal to Q delta V. This side of the equation, right? So let me get back to my... Work is equal to Q delta V. Well, what is the work? Work is equal to force times distance, right? And earlier we said that the force that you feel in an electric field, that a charge would feel, is equal to the charge that's in the field times the field. So it becomes the charge that's in the field, Q, times the electric field, E, times the distance, D, equals Q delta V. Change of voltage. Just like that. Now we have an interesting equation here.
Where did E come from?
That's
It came from the force. The force that a charge
Force
feels,
equals Q charge times.
right, the force that a charge Q feels in an electric field is Q times that electric field. So if you know the value of an electric field,
And the E is electric field, right?
that's correct. If you know the value of an electric field, then you can multiply that value times a charge that you'll put in that electric field, and you'll get the force that charge will feel in the electric field. Now, when we're done here in a second, we're going to write down all the equations we've learned so far and show you that there's not as many as you're thinking that they are, and help you to understand where each one of them is used, kind of like we did in the first semester. But now we've created a new equation that has two things in it. It has it has four things in it. It has charge in it on each side of the equation. It has electric field on one side, distance on the other side, and delta V. So now we get some relationships. First of all, notice that the charges can be dropped. No pun intended. But if we drop all charges, because we divide by Q on both sides, we get E times D equals delta V.
And that just figures out the strength of the field.
You can actually calculate the strength of the field if you know the voltage. It's delta V divided by distance. What's the distance?
Your R.
Yes, essentially yes. It can be R, but what it's going to be really is it's going to be the distance that you travel to go from one voltage to another voltage as you go through a voltage change of delta V. So essentially it's the distance between the points where those two voltages in delta V are located. So delta V, remember, is two different voltages. Delta V equals V final minus V initial. And these are two different places in the field. So the D is the distance between the two different places where those voltages take place, where those voltages are. So that's the D. And you could think of it as the R, but it can be that, but it's not always that. So it's kind of confusing, but not too bad. So essentially we can calculate our electric field from a change in voltage, from a change in potential over a distance. We can also calculate our voltage between 2 points right here. In this book, in the book it's voltage equals E times V. But it's essentially just taking this same equation here and saying the voltage between 2 points, A and B, for example, between points A and B is equal to the electric field that's in the region times the distance between A and B. It's pretty simple. However, this only works if the only reason that this is working is because we're assuming that our electric field is the same everywhere. We're assuming that there's nothing changing as we go from distance from point A to point B. If the electric field stays the same between A and B, this works. If it's changing, it doesn't work. So this works for what we call a uniform electric
So
field.
A to B is the distance between one point to another.
That's the distance between A and B. That's right. DAB is the distance from A to B. And all this theory is kind of confusing, I admit. But let's do something again. Let's do another example to show that applying it's not really all that difficult. In this example, we have an electric field in dry air, which is as strong as it can be. So dry air supports a maximum electric field of 3 times 10 to the 6 volts per meter. So that's another way of measure, another unit for electric field, volts per meter. So if we have what was it, 3 times 10 to the what? 6th. So 3 million. 3 times 10 to the 6 volts per meter of electric field. That's our E. And it's a uniform electric field. And it says above that value, the field creates enough ionization in the air to make the air a conductor. This is what happens when lightning occurs. So if this is a lightning situation, what's going on is you have a cloud up here that has a bunch of electrons on the bottom of it, and the Earth, which the electrons are running away because of all those electrons in the cloud, so it's positively charged underneath. And you have this uniform electric field that's going from Earth to cloud.
But that's not lightning.
No, it's not yet. But this uniform electric field in here is equal to this, 3 times 10 to the 6 volts per meter before lightning strikes.
All right, so E is, what is E again?
E is electric field,
Okay.
and we're using the units volts per meter. So it's how many volts, it's how many volts that is separated by how much
Volts
distance.
per meter is the unit of measure for an electric field.
That's correct. It is the unit of measure. That's correct. So the voltage is caused by the charge, and the per meter is caused by the separation between the charges, right? So that's the volts per meter. Now, this electric field has now reached this 3 times 10 to the 6 volts per meter, and above that value, what happens is that the particles out here, usually nitrogen molecules, end up getting ionized. In other words, this electric field is so strong that the electrons feel a force that rips them right out of their atom, rips them right out of their molecule. So all the air in here becomes charged, and then once it's charged, it will move one way or the other. When it becomes positively charged, it will move up here, and negatively charged, it would move down here, but in any case, it's charged.
Is that a standard number for that? Whenever electricity actually jumps?
This is the electric field at which dry air will conduct electricity, so the electricity can start jumping. And once you've got those positively charged particles out there, or negatively charged particles, then electricity can flow either way. And that's exactly what happens, is that you get these positively charged particles come up here and grab electrons, and then they move down there.
When the
drop them
electric
off.
charge moves in dry air.
At that number, it changes, but that's a number that they'll give you in the homework or the test if you really use it. But we want to know what is the maximum voltage between two parallel conducting plates that are separated by 2.5 centimeters of air. So what is the voltage out there? So this is the field. What would the voltage be if there was only 2.5 centimeters of air in between the two plates, or between the cloud and the ground? In other words, if the distance D was 2.5 centimeters, and the electric field is
3 million times 2.5.
exactly, well, not 2.5 because it's going to convert to meters. So you take 3 million times 0.025, and you would get the amount of voltage you're going to get. And what do you get when you do that? You get 3 million times 0.025. You're going to get yeah, a quarter of 33 million. Okay, so that is, so in the end, it actually ends up being 75 kilovolts, or 75,000 volts of voltage between those two plates if they're only 2.5 centimeters apart. What if these two plates are in a machine designed to accelerate electrons, like the machine that we were talking about before? In the machine that we were talking about before, we had two plates, one with a hole in it, right? Let me erase this.
It would have the same act on it as friction would on two objects against each other, right?
So in this thing, they say we have parallel plates separated by 4 centimeters, and the electrons gain 25 kilo electron volts of kinetic energy. We want to know what is the electric field between those two plates. So let's try to figure that out. So instead of figuring out the voltage, they give us the voltage. We want to figure out the electric field. So we have our plate here that is negatively charged, our plate here which is positively charged, and we're going to accelerate electrons out this hole on the right side. Let's show this picture to everybody. They give us 4 centimeters, 25 kiloelectron. Well, that's all right. So here we go. We've got this is our apparatus for this. This is an electron gun. In an electron gun, essentially the electrons jump off of the plate, but we have electrons that are now going to move this way, get accelerated out here. And they've told us that the voltage here, the voltage difference, or delta V, is equal to 25 kiloelectron volts, right? That's the delta V here. And they want to know what is, and they said it's 4 centimeters difference here, right? And they want to know what is the electric field. Well, here's our equation. Electric field equals change in voltage over distance. So we take our change in voltage, 25 kiloelectron volts, divided by 0.04 for 4 centimeters, and we're done. What do we get? 25 kiloelectron volts divided by 0.04 is like multiplying by, well, that's right, but it's like multiplying by 16, I think, or no, 25. What is it? I don't know. It's like multiplying by 25. 0.04 is 1/25, right? So we take our 25 kiloelectron volts, and we divide by 0.04, which is the 4 centimeters, and we hit enter on that, and we get 625,000. So it's like multiplying by 25. So our electric field is 625,000, or 625 joules per coulomb, or 625,000 volts per meter.
How did that big of a number? Because of the K? You got
Yeah, because it was 25,000 divided by 0.04, which is like multiplying 25,000 by 25. So it's 625,000. Yep. So 625,000 volts per meter for our electric field in that situation. That's not, I mean, 625,000 volts is not a big deal. There's 625,000 volts on the power lines that are on those big tall towers between here and Sutherland. There's easily that much. There's probably more than that. So it can be done, and you can really get electrons moving at those speeds. But remember that the clouds, when they were up at those high voltages and had the big electric fields, the clouds would cause ionization in the air and cause lightning to strike. So when you make something with really high voltage, you have to put it on a high tower. And it's not to protect people from touching it, although that's another good reason, but it's to protect it from striking lightning to the ground. Because if you strike lightning to the ground, not only is it dangerous, but you're losing power. You're losing energy that you want to use to make your toaster toast bread or whatever. So you have to make the bigger the voltage, the higher the tower every time. And also the further apart the wires have to be, individual wires, if there's a voltage difference between the wires, which there usually is. So the smaller, the voltage when it comes in at your house is just a couple hundred volts. Not much. A couple hundred volts coming into your house. So you can walk right up to that. It won't jump across to you. Couple hundred volts, it's not going to jump through air anytime soon. You can grab onto the wire. In fact, if it's got rubber coating on it, the rubber coating is enough to prevent that from jumping to your hand. I wouldn't recommend it, just in case that rubber coating is not doing so well, but because it can kill you. So don't try it. Don't mess around with the power lines coming to your house. But it's at a couple hundred volts. It's not going to strike lightning, so it doesn't really matter. You can bury it underground. It's fine. But at thousands of volts, that stuff will strike right through rubber and right through people and right through everything else. So you got to be careful. You got to put it up high so it doesn't strike, it doesn't come down. All right, so that is that. Let's go back to our book and see what we've got next. See what that puts us through section. It takes us through section 3 or 4, I think. Nope, we're on 3 now. How many sections do we have? 7 sections. Point charge. So this is the last one that we'll do really quick, and then we'll move on to the last 4 sections next time, which have to do with essentially capacitors, electric fields.
Will we do the lab tomorrow?
Yep, we'll do a lab tomorrow. Actually, we'll do the next 2 sections really quick before we're done so that we can do that lab properly. Then in section 3, we make the calculation for calculating the potential due to a point charge, which I showed you earlier, which is really quite simple. You take the electric field of a point charge and you multiply it by the distance that you would have to go to get away from that point charge, which would be the R, and you end up with this equation.
R is a great distance,
Yes.
but it's considered radiant.
Yes. We use R for distance in this case because R can be measured in any direction. So we don't. That's why we don't use X or Y, because it's not in any particular direction. So we use R, which R can be rotated in any direction for radius. So anyway, remember the electric field for if electric field times distance equals voltage, then voltage equals electric field times distance, which is the same thing, right? Sorry, confused the heck out of voltage.
Divided by E.
Voltage equals electric field times distance. So if this equation is true, then we should be able to use this to calculate the voltage around a point charge, because we know that the electric field around a point charge from the last chapter looks like K times Q. Well, we use a big Q for that. So K times the charge of your point charge, whatever it is, Q, divided by R squared. So if we multiply by the distance now to get the voltage, we do K times Q over R squared times R, and then one of those cancels with one of these, and we get voltage now equals K times Q over R. So it behaves a little bit different than the electric field. The voltage doesn't drop off so quickly as the electric field does. That may seem a little counterintuitive, but it actually works out mathematically. So what this means is that you can now calculate how much voltage you get, or how much potential there is, and then of course then you can calculate potential energy if you calculate potential. You can calculate the potential around a point charge. So what does that mean for us, practically speaking? We have a charged particle here that has some charge Q equals, let's say it's 2 microcoulombs or something. It has, I don't know, a fair amount of electrons missing from it. Positive 2 microcoulombs, it's got a lot of electrons missing. So it's a positively charged object, which means it has this field that's moving away from it like this. And we can calculate the value of this field, because the value of the electric field of this charge Q is going to be K times Q over R squared for whatever distance. So let's say that we want to know the electric field at 0.5 meters away from this thing. Well, then we plug in 0.5 meters into here, we plug in our Q into here, we plug in our Coulomb constant, we calculate the electric field. Right? It's that simple. I keep forgetting to put my screen back on here. How do I put my screen back on?
So it's almost identical to how friction works between two objects.
What's that?
It's almost identical to how friction
No, friction, no, it's not anything to do with friction.
works. I know it doesn't
it's
have
not
to do
anything
with
to
it, but it's similar in the way that it works. It takes away how much force it has or how much energy.
Oh, the further you get?
Yeah.
Yeah, the further you are, you have less and less energy, less and less electric field, less and less force, that's true. But the thing we wanted to show here is that the voltage can also be calculated. You take the K times the Q, and then you just divide by R. So in this case, you'd have 0.5 squared for the electric field. You'd have a lot less electric field. But for voltage, if you're calculating the voltage, you would just be divided by 0.5 instead of 0.5 squared.
All right, so E equals E times electric field times distance equals change in voltage. So we're not figuring out the change in voltage because it's point, we're just want to be, the A and B goes away.
Yeah, this essentially tells you the difference between zero voltage and the voltage at this point.
Okay, so we're assuming one point is 0 voltage and the other point would be.
Yeah, we're assuming that way out as far as you could get away from this point would be 0 voltage, and at this point it has some particular voltage compared to that 0 voltage. So I think I know what you mean when you said voltage equals E times D was kind of like friction. Okay, so in that case, yes, you could think of it. The further distance you go, the more drop off you have in the electric field, and that is true. But it's not necessarily. I mean, mathematically they're related, but physically they're not related. So the mathematics looks similar, but the physics is nothing similar. So anyway, this gives us now what we call voltage. Why would we care? This is potential, voltage, whatever. Why would we care? This actually has implications because of the way the electric field and the voltage are represented. So let's look at the point charge specifically and do some calculations for voltage. So here's our point charge. How do I make this screen all the way big? I can't, for some reason it decided not to go back to its full size. And I can't even make it big. This is so annoying. There we go. Okay. So here's our point charge, whatever it is. We'll give it a positive point. It's a positive point charge with charge of Q. It has these electric fields that are going, this electric field that's going out away from it like this. And remember, the strength of the electric field is determined by how far apart the lines are, right?
And that means the field's going away.
That's right, because it's a positive charge, the field points away from it. That means if I put another positive charge out here, it would be pushed away parallel to these field lines, right? So it would be pushed away like that. In fact, if I put it in between here, it would be pushed away parallel that way. But so it's always equidistant from all the field lines around it. But anyway, if I calculate the potential, V equals KQ over R, I get something very different, very interesting. At every distance R away, so let's say 1 meter away, let's say that this is 1 meter away. At 1 meter distance away, everywhere around is charged. So 1 meter this way, 1 meter this way, 1 meter this way, 1 meter this way, I get the same voltage. And so all along this circular path, I have the same voltage. Because it's the same charge, the K is always the same, and R is 1 meter. And at every distance, out here, at 2 meters, I get the same voltage. At 3 meters, I get the same voltage. And look at the relationship between the field lines and these lines of what we call these lines of equal potential, or equipotential lines. So these equipotential lines and these field lines have a graphical relationship. What is the graphical relationship? Graphically, what is interesting about this? These lines
They're
are
in a straight line. It increases and decreases in a straight line.
well, you can kind of that's one way of describing it. But graphically, if I'm going to describe this, and if I drew this better, you'd really see it. But on most of these places, you can see that the angle between the field lines, which are green, and the potential lines, which are purple, is always 90 degrees. And mathematically, that's actually much easier to prove. I mean, using calculus, we can prove that.
Yeah, but it's only a straight line that's where they connect.
Only where they cross,
Right.
where they actually connect or cross. But that's interesting because one of these things is easier to measure than the other. Equipotential is very easy to measure. It's very easy to measure voltage. But electric field is a vector. How easy is it to measure vectors? It's much more difficult because they have a magnitude and a direction. A voltage just has a value, and a voltage is not a vector. A voltage is just a number. It's just a value. It's an energy. Energies aren't vectors. Well, it's related to energy. So the voltage is very easy to measure. You take a voltmeter and you plug in one side of the voltmeter to a 0 voltage potential, and then you just take the other one and start touching it in places where your field is and see what the voltage is. And if you can find a circle where there's an equal voltage all the way around, then you found an equipotential line or an equipotential surface in 3 dimensions. And then you can draw that line and say, I know where the field's going, because the field's always going to go perpendicular to that.
You know, this isn't 2-dimensional, it's actually 3-dimensional.
Yeah, it's technically, this would be 3-dimensional. We're looking at a cross-section. But in 3 dimensions, we could do it as well. It'd be a little more complicated, but we could do it. But the point is that if we can measure something easily and then extrapolate something else from it easily, we like that, right? And that's exactly what you're going to be doing in your lab tomorrow. In your lab tomorrow, you're going to be creating electric fields on paper. And then you're going to be measuring voltages on the paper to find these equipotential surfaces, which will look like equipotential lines on the paper because we'll be looking at a cross-section. And then you're going to draw the electric field. And now that you know how these things are related, and you know kind of what's going on, it'll be easy. If this was a negative charge, what would be different about this picture?
Well, I think
Maybe go
The field line would be pointing in, but you would still have equipotential surfaces. This one might be 5 volts, this one might be 7 volts, this one might be, whatever. Most likely, and it could be negative 4 volts. You can have negative voltages, right? So it could be negative. Could you get to a 0 voltage?
Is it negative?
What's that?
When it's an electron, the negative, when it's an electron, is it considered negative?
So what happens is because we specifically, remember when it comes to potential energy, we have to choose our 0 point. And we usually choose our 0 point in electronics to be a point that is as far away from our charge as possible. So when we're using a meter, we use a common, usually. When we're using other meters, we might use ground. But essentially, that's going to make potentials from negative charges become negative potentials. Potentials around negative charges, potentials around positive charges become positive. And then, of course, if you have a combination of both, which you can do, then it will change from positive to negative, and you could even get 0 in between.
So what's the distance between the lines, right? Not from the voltage, but the force, right? That's how many
So the
lines
distance
are.
between the field lines tells you the strength of the force. The further the distance, the weaker the force, right? With the potential lines, if you draw equal potential lines that are equally spaced in voltage, so if each one of these is 5 volts difference, so this is 5, let's say that this one's 20 volts, this one's 15, this one's 10, and then the next one is 5, then the distance between those lines would tell you field strength as well. The closer together they were would mean stronger field.
But you'd have to know the difference, the distance
But-
between them.
Yeah, but they would also have to be equally spaced in voltage. So they'd have to all be 5 volts difference. This one would have to be 20, this one would be 15, and this one would be 10. This one would be 35, this one would be 33, this one would be 31, if you spaced them 2 volts across. Apart. If you do it that way, then the closeness of those lines, this is essentially like a topographical map. It's the slope lines on a topographical map. The closer together the slope lines are on a topographical map, what do you know about that area? It's very steep. And it's exactly analogous to this. Because the closer these lines are together, then the sharper the change in voltage is, right? Or the sharper the change in the electric field is, which means the more, and truthfully, if we're going to draw these lines correctly, if these were equally apart, let's say this was 20 volts, and this next one was 15, this next one out here, to be equal, would have to be further apart, because the further you go away from a charge, the more it drops, the more the electric field drops off, right? So you would get a much, much steeper climb as you get closer and closer to the charge, because you get more and more force between charges as you get closer and closer, right? So it looks like a topographical map. And they have much better pictures, of course, in the book, which I can't show you, but you can look for yourself. But these are called the equipotential lines and the field lines of an object, and they're very useful in let's see, that's in the next section actually. There we go. They're very useful in drawing the shape of field lines, figuring them out. This is especially true when you have many, many charges or shapes of charges that are weird. We've been dealing with point charges, but if you have an object that is not a point charge, that has a different shape to it, you're going to get very different things. So here are the field, here's one that they show you in the book, which is a dipole, they call it, in physics, where you have a positive charge and a negative charge fairly close together. And what happens in this kind of a situation is you get equipotential lines. So let's say that we're going to draw a line, we're going to draw an equipotential surface, we're going to come in and measure the voltage around this guy. If we were just looking at the positive charge, and the negative charge wasn't there yet, we would get, let's say we did 5 volt differences, we would get one here, and maybe one here, and as we went further out, they would get further and further apart. But it would be pretty symmetrical, and that's not very symmetrical. But they would be concentric. They would be circles that are centered, exactly on each other. But when we bring in a negative charge, it has similar, and it's maybe the same amount of charge, just negative. It would have similar circles out here.
But whenever they touched, would they pull each other toward you?
Well, no, because they're not allowed to touch. These things can't touch. If they touch, then they're infinitely close together, which means you would get infinite voltage, which would mean infinite energy. You can't have infinite energy. So they can never touch. It's not allowed.
Say that to a nuclear bomb.
Nuclear bombs definitely have a finite amount of energy, not infinite, not even close. So what happens then? What actually happens? What happens then is as these potentials, which are different potentials, because these are all negative potentials, these are all positive, they're not going to like to be near each other actually. So they actually push away from each other. So instead of getting nice symmetrical circles around these guys, they actually push away from each other just as if they were charges.
Except potentials of the same kind would attract, and potentials of different kind would repel.
It turns out that all potentials,
They like each other, but not that much.
it turns out the potentials of charges do kind of the opposite that the charges themselves do. So it's similar, but
Like potentials
So let me show you. So these ones, because they're positive and negative, they can't become the same thing. They're not going to become the same thing. You can't change a positive to a negative and a negative to a positive. And so what happens is they push away from each other, so they get this slightly weird shape to them. You still get this spreading out that gets bigger and bigger the further away you go. The distances still get bigger and bigger the further you go away from it. But they kind of push away from each other, and eventually you get so big that you end up sharing a line in between. Or in other words, you have this thing that's in between that is, you have positive on this side, this would be 20, and then 15, and then 10, and then 5 maybe here, and then this actually ends up canceling out with this one. The 5 and the negative 5 cancel out in the middle, and eventually it becomes 0. Yeah, you actually get a 0. You actually get a zero potential in the middle. In other words, the negative potentials and the positive potentials kind of cancel each other out in the middle.
So this is, all right, so you're talking about a positive and negative charge, right? And you're talking about what medium is this charge in? Like,
Whatever, it can be in vacuum, it could be in air, it could be in paper, it could be in water. Doesn't matter.
so we're just talking about charges without talking about electrons and neutrons and
That's
protons.
right.
And,
So, but what would the fields look like? Remember, what do fields do? What do the field lines do compared to these are equal
They
potentials?
always come out at a 90 degree.
They come out at a 90-degree angle from the charge, but they always cross these other potential lines at a 90-degree angle as well, right? 90, 90, 90, 90, and it's coming out and going this way from the positive charge. What does it do on the negative charge?
same.
Goes into a negative charge at a 90-degree angle, right? So the field lines actually start to look much different than they might have looked before. And then on each side of each side of these things, we're going to have one that comes in from infinity, one that goes out to infinity and is not affected by the other one. But everything in between, they're going to join forces and create this field that goes from one charge to the other charge. So that if you put an electron in here, it would follow the field lines, it would get repelled away from this one, follow the field lines backwards to this one. If I put a positive charge in here, it would do the other thing, right? And if I put it over here, what would it do? It would go loop around here, right?
So the fields can't touch, but the electrons can.
What do you mean?
Like 2 electrons, like the strength of that field would be how many electrons was in the negative, and how many protons
Two,
was in the positive.
You mean the electrons, like the electrons that are causing this negative?
Yeah.
They can't ever touch, but they can be grouped together. You can create a negative charge by
So really, really, in the material, because that's only 1 electron and 1 proton, actually, it would look a lot different.
Sure. Well, yeah, it could be 1 electron. It could be 1,000,000 electrons. I mean, just call it 1 charge and give it a value of the charge of 1,000,000 electrons. Whatever. What happened? I mean, this is what we call a dipole charge, and you can see that the fields take on these shapes, and then you can have charges traveling along curves. Well, imagine if you put on all kinds of charges. You can create all kinds of shapes and create all kinds of paths for charges to follow. And this is what we call electron optics or charge optics. We actually guide particles using electric fields. It's kind of cool, and then you can do all kinds of stuff with this. This is one of the things that makes.
Is that kind of how hadron, or whatever that thing is?
Yes, they definitely use these techniques in the Large Hadron Collider, and in all particle physics, they definitely use these techniques. And the field, let's say that we change what we're looking at. I keep forgetting to go back to my desktop here. No, that's not what I wanted to do. Here we go. So that's the field of this dipole with these electric fields at 90-degree angles to the electric potentials, to the potential lines. But what if we change one of these signs of these charges? What happens? We get a whole different kind of thing going on. So here, let's say that we have two positive charges now, and we start, and let's say they're the same charge, and we start measuring voltages between these two charges. What's going to happen? Well, this one's going to have a 5-volt line, right? And this one's going to have a 5-volt line, a 5-volt circle. And if I go further out and measure, 4 volts or something, if I measure 4 volts out here, it turns out that these things are going to start attracting each other because these voltages are the same. So these would get close together. But eventually there's going to be a point at which they merge, where the voltage around here never comes to a point in here. So this might be my 3 volts. 3 volts here might just make a shape around here like this. And what's that going to do to these fields? Well, these fields, remember, and actually there's never going to be these in between. These will never happen. These will always form this if you look closely enough. Sometimes it's hard to see them because they get kind of close together here. But they're always going to do this in between.
Now, here's how you dictate how your strength of your fields can change.
Well, what this is going to dictate is it's going to dictate where the field lines are going to go. Field lines always have to do what with the potential lines? Cross a 90-degree angle. Will you ever get a field in between here?
No.
Never, because it never crosses the electric potential. What does that mean if you never have an electric field from here to here? What does that mean the electric field isn't here? 0. There's no electric field between these two things. However, where is there a field? Right here, and right here, and out here, and out here. But the closer I get towards going towards the other one, those electric fields do what? They repel each other. And that's what determines whether this thing repels, these two charges repel each other or reject each other, right? These electric fields never connect to each other, which is very different than the other one. They actually repel each other, right? So that is another example. Now let's take a look at what happens to weird shapes.
Is that still called dielectric field?
No, it's not. The dielectric is very different than this. But we meant the dipole field.
Yeah.
This is not called a dipole field. This is, I don't know if they have a name for that.
Dipole field is when two opposites.
Two opposite charges, that's correct. But let's look at something different. Let's charge a dog. Here's my dog. Nice dog. It's got a big chin. Here's my dog. I'm going to charge up my dog. So, take my dog and rub him with plastic or something.
Rabbit fur.
No, the wrap, that'd be fur on fur. We need to rub him with saran wrap. Right? Wrap him up in saran wrap and then unwrap him real quick and then he'll be charged up. Right? So we charge up my dog and let's say that he gets a negative charge all over him. Each one of these negative charges is going to create its own field. And as we start to measure voltages, what we'll find is that we'll get an equipotential that is roughly kind of shaped like the dog. Turns out. It depends on how the dog gets discharged. If we don't charge its head too much because we don't want to suffocate it with saran wrap, that's going to change it, isn't it? The electric field is going to change here because there's not very charge. So we're going to get some potential that's going to be different. It might come through here. And it might actually even do this because we might have charge on the inside of the dog. But we just measure that. And then how do we figure out where the field's going? We do the same thing we did before. It's going towards negative charges and it crosses at 90-degree angles. Wherever we have sharp turns, it's going to really change things, isn't it? So like right in here, we're going to really get a big change. The electric field's going to do some weird things when we have
It's
sharp
going to
turns.
be stronger and then go out towards the head.
Yeah, it'll come out here. You have lots of electric fields coming out of the mouth, right? But we can actually figure out where those charges are going. Now, if my dog was made of metal, no matter what, the charges are going to spread themselves out in a very particular way. We already know how this works with metals. We looked at this kind of. On metals, charges like to congregate near corners and sharp edges. They like to congregate at those corners and edges and corners and things like that. And then they spread themselves out pretty evenly on those spots that don't have corners. A little more close on these corners. And then as you measure these things, you're going to see that this is going to be the same here. You're going to get this shape that roughly follows the shape of that charge distribution. And with metals, it's distributed nicely. So where you have corners.
5 volts, you'll be able to read it front or way.
Yep. And then you can create your fields. Wherever you have sharp corners in your sharp turns in your potential, you're going to get more field lines to try to make those become nice and 90 degrees. Where it's more spread out, and you won't have to do so many. It'll be easier to make it 90 degrees, for example. And then you're good to go. So anyway, I think that gives you enough to be getting on with here, to get started with homework and to understand the lab tomorrow. You'll actually learn quite a bit during the lab. I think it's a good lab for understanding how equipotential lines are related to field lines. And when we come back, we will talk about capacitors, which are a particular type of device that take advantage of these relationship between fields and potentials. So we will break until next week. I mean, not next week, until this Thursday. Tomorrow we will have lab, and then Thursday we'll finish the rest of the chapter. Do get started on homework and everything else. Now, do either of you have any questions from the last homework that you want to answer? Are you going to
I
go?
want to start working on it Sunday, and then it's closed.
Okay, so you're going to go work on it some more? Okay.
Right, have no choice.
Okay, go work on it some more. Send your questions to me or whatever.
Going home?
No, I'll be here for at least I'll be here probably for at least the next few hours. So if you want to work on it again here, you can. All right, so let's go ahead and stop our recording. Let's post that online for everybody.